Hello everyone, welcome to the BMS YSP project presentation. In this project, I use the SpiderCat catalog with Gaia DR3 to identify companion and nearby target stars and study their future motions. The idea comes from the Stellivore hypothesis. Some accreting binary systems may eventually approach another star. Using Gaia proper motions, we can project their future trajectories and identify which stars, if any, they are moving toward. A quick background on pulsars. A pulsar is a rapidly rotating neutron star whose emission can produce very irregular pulses. Millisecond pulsars are especially fast rotating pulsars. Spider pulsars are millisecond pulsars in closed binary systems with very low mass companions. They are broadly divided into black widows and redbacks. In this project, we are particularly interested in the motion of these systems and the stars they may encounter. Our starting point was Spider Cat, the dedicated catalog of spider pulsar systems. We first understood the pulsar and spider system information, then matched the spider systems with their Gaia IDs. And after a series of steps, we got a cleaned working list of Gaia identified companion stars. At this stage, we are connecting three pieces of information. SpiderCat tells us which spider systems and companions we are interested in. Gaia tells us where these stars are and how they are moving. And the pulsar timing information provides additional information about the pulsar motion. So the goal is to bring these data sets together into one consistent kinematic analysis. So for that, the key quantity which we need is proper motion. Proper motion is the apparent angular motion of a star across the sky, usually measured in milliarc seconds per year. Gaia gives us the proper motion in two directions, right ascension and declination. By using these, we can extrapolate where a star will appear in the future and determine when two objects come closest to each other. The analysis follows a systematic pipeline. We begin with the cleaned SpiderCat list, recover the Gaia IDs, and search Gaia DR3 for nearby stars within 10 arc seconds. Using Monte Carlo sampling of position and proper motion uncertainties, we propagated the motion in 2D and calculated separation over time. We then separated past and future encounters, focusing only on future encounters here. So instead of getting just one predicted trajectory, the Monte Carlo gives us a distribution of possible trajectories. This is important because Gaia astrometry has uncertainties and correlated errors. In this example, we can see the angular separation initially decreases, reaching a minimum of about 6 arc seconds around 800 years, and then increases again. The dot marks this minimum, so this is the closest future encounter predicted for the system. Once we had a targeted stars, we wanted to know what kind of stars they actually are. From Gaia, we extracted parameters such as effective temperature, surface gravity, BP, RP, G magnitudes. Effective temperature tells us about the star's temperature, while surface gravity helps distinguish high gravity main sequence stars from low gravity evolved stars. We can also use BP minus RP as a color indicator of stellar temperature when temperature measurements are unavailable. We also ask whether these target stars are single or part of binary or multiple systems. There is no established preference yet, but we predict that spider pulsar targets may be more often single than random galactic encounters. This is a prediction, not yet an established result, which is why we need the control experiment. Of the stars with available temperature and surface gravity measurements, most are consistent with main sequence dwarfs. However, there is an important caveat. Many stars do not have both temperature and gravity measurements available, and Gaia's GSP fault parameters are based on a single star assumption. But seeing lots of KNM stars does not automatically mean that spider pulsar targets are unusual. KNM stars are very common in the galaxy, so the real question is, do we see an unusual fraction of them compared with the right control population? And that is where the next part of the project comes in. Our next step is therefore to create a control sample. We plan to take 23 random Gaia stars, apply the same close encounter procedure, and repeat this at least 10 times to obtain meaningful statistics. We will then compare the stellar types and multiplicity of these random targets with the spider pulsar targets. So our current sample is dominated by cool KNM stars, but we don't yet know whether that is unusual. Ultimately, the goal is to determine whether spider pulsar target stars are genuinely different from the stars we would expect to encounter around ordinary Gaia field stars. So the control sample and multiplicity analysis will allow us to test that question properly. And with that, I'll conclude. Thank you for watching. And if you have any questions or comments, you can drop them in the comment section below. Thank you.